Good afternoon, everyone. My name is Kensuke Take, and I think many of you are speaking Japanese as a primary language. So I put all these. You can see Japanese everywhere. So if you have any questions, you can ask me later in Japanese or English or whatever. So okay, back to the topic. I'm going to talk about safe randomness, theory and practice. And my name is Kensuke Take again, and I've been working as a freelance engineer for 5 years. And I've been working in the software industry since 1990. So this is about 28th year or something. Okay, in this talk, I'm going to talk about randomness. Randomness, okay? So what is randomness? There are many aspects of randomness, but the most important aspect of randomness is unpredictability. Randomness, which is predictable, is no longer randomness. Okay? And randomness is essential for secure operation. So, how do you use randomness? When you generate password or public key, shared key, private key, you have to generate them from random numbers, truly random numbers, unpredictable. Any kind of predictable passwords, no predictability should be in the password, okay? And randomness can be used for obfuscating timing. Timing obfuscation is important for executing, for not revealing characteristics of code. And if timing is captured by the attacker, there will be some sort of exploitation. And there are many kinds of that kind of attacks recently. And if you're going to use multiple resources equally but unpredictably, so it's hard to pronounce, you can use randomness. So in algorithm, randomness is represented as random numbers. Or better say, in computer algorithm, everything is represented by numbers, after all. So this is so trivial. So let me talk about my past works on random numbers. I made some contribution to RNOTP along with called RabbitMQ and many other software systems. And I did improve the random number algorithms. And I made some implementations over here, like random module, SFMT, and TinyMT for RNOTP. Okay, before going to the old stuff, let me show you a sort of bad algorithm example. This is actually from JavaScript, and it's in V8 in browser in 2015. And there was a bad algorithm in JS. You see lines, horizontal lines on the mapped patterns over there. And those horizontal lines means predictability, not unpredictability. It's absolutely predictable. And this was not revealed until the V8 people kind of panicking in 2015. So they changed the algorithm to a much better one called XOR shift. And that's the right one. So the right one is the better algorithm on V8, and it's now on the V8, so you don't have to worry about this anymore. But this kind of programming mistake is so trivial when you deal with random numbers. So you have to be careful when you program on random numbers. You have to check the results by mapping random numbers like this. Okay, and there's a story about the legacy RNOTP random module. The old random module was with the algorithm in 1980s. It was actually in the Byte magazine in 1982 or 1983 or something. It's all designed by 16-bit algorithm, and it's called AS183. And I wrote a code in C to exploit all the AS183 combinations in just 8 hours on Intel NUC. It's a C code. and I've already put it on the GitHub, so you can take a look at it if you want. And after showing this, it immediately became a security issue between our OTP team people. And our OTP team people asked me to write something much better, so I helped them. And it's now the de facto standard. So if you are using Erlang OTP 19 or later, the current latest version is 21. You don't have to worry about this, but old code in Erlang still contains random module code, so you have to be careful. But if you really pursue random numbers, software contribution is not enough. So I contribute something by hardware. So why hardware? Because randomness is hard to find in a computer. If you program, if you write code, if you do anything on the computer, you are doing predictable things. You have to make your computer predictable, or your machines predictable, your software predictable, or otherwise it will be full of bugs. So computers are predictable hardware, and it's programmed and do what you want to do over here. So it's on the absolutely opposite side from randomness. But still, you can find some sort of randomness in the computer, because computer is a machine, and a machine is actually a physical thing. And if you run a physical thing, you cannot get rid of uncertainty. This is the law of physics, so you cannot get rid of any kind of uncertainty for all. But the randomness sources, not much. I'm going to explain a few. The CPU clock jitter, the frequency difference, frequency change, subtle frequency change would be a source of randomness. And if you type keyboard, your habit of keyboard typing or patterns might be a randomness. And if network packet timing, if you measure timing of the network packets, that would be a randomness. And if you seek hard disk or any kind of storage, the timing difference or the distribution of timing would be randomness. But those randomness are unfortunately not so much. So modern computers, including those Linux machines or Mac OS or Windows or FreeBSD, almost all machines have processing flow like this shown over there. And in short, all of those random numbers or random entropies, or better say randomness sources, are once stored in a randomness pool. And the pool will be used by the cryptographically secure pseudo-random number generator. And the generator will give you /dev/u random. And if you are trying to use /dev random, stop. Don't use it. Don't use it on the Linux, because /dev random is very actually accessing to the very scarce resource, and I don't recommend it. Use /dev u random. Okay. So I did some experiment, and the experiment in a small Internet UC server at my house. Without no keyboard is connected, and I think the only random source is network packet, or maybe CPU clock. But the randomness available in the system is so small, 0.62 bit per second, 0.62 bit per second. And this is so small that every password might be a length of at least 100 or maybe 500. Or even longer, bits, I mean. And if the system gives you only this sort of randomness, it is very, very, how do you say, predictable. So you cannot expect much from the normal computer without any kind of hardware attached to this might be a problem. So the obvious conclusion is you need additional randomness. Why? Because security depends on the unpredictability. I repeat, security depends on unpredictability. And secure operations consume randomness. And it's about consuming all those. It's about consuming all those bit stream, random bit stream, and you use it for generating randomness, some sort of keys or passwords. And so you have to have a steady flow of randomness supply by hardware. And the variety of randomness is still limited. So to obtain such kind of randomness, you have to use some sort of physical phenomena, such as thermal noise. Thermal noise is there everywhere. You can find it in molecular movement, Brownian movement or something. And you can find it in the air as a part of the air wave or radio wave. And there's another source called avalanche noise of semiconductor junction. If you use a specific circuit of diode or bipolar transistor, you can find the noise over there. And you can also use the timing jitter of oscillation circuits, which means free oscillation circuits. The free oscillation circuit actually changes its characteristic, and it's random. And the mechanism is quite similar to the thermal noise, so it's actually quite similar to thermal noise. So, okay, this is, whoops, this is a physical random number generated dice, which I exhibited on the Maker Faire Tokyo 2016. And this dice device is actually using the physical random number generator and generates a number from 1 to 6. Oh, good. Okay, he will show you. Thank you. Thank you very much. And actually, this device is in this device, I use the same random number generation circuit for the my dedicated random number. Sorry, my English is so bad. Physical random number generator for Arduino, and the generating speed is about 10 kilobytes per second or 80 kilobits per second. And this is the circuit. This is a circuit over there, and there's a two right here. This one is the semiconductor circuit generating avalanche noise. Okay, and all the other triangular inverters, these are actually analog and digital amplifiers, so that the level of the output will be converted to the digital level. So, thank you very much. Maybe you can put it down over there. And I'm going to show you another device. This is so plain, and this is just a dongle. But actually, this is what I've been using, testing for 2 or 3 months. It's called Infinity Noise TRNG, and this is thermal-based noise. The price is about $35 per device. You can buy it on a crowd supply, and there's a supplier who builds this in Germany, I think. And the good thing about this is that this circuit is completely public domain, in public domain. No patent, no software copyright. So all the drivers are in, so this means you can change whatever you do, and you can, there's no license restriction. And about this device, there's one good thing about this device is that this device has no computer. So you cannot hack this device by software or injecting software into this. So this is kind of more secure than my Arduino driver. Arduino device. And the generation rate of the random number of this device is about 40 kilobytes per second, or 320 kilobits per second. And let me show you how this works in a very short time. This part on the left, that part is FTDI chip, which is an interface between the USB and the software device. USB and the hardware. And computer just controls that device so that it would obtain amplified noise from the right part of the circuit, right half of the circuit. It's a noise amplifier and a noise generator. It's a kind of feedback amplifier. Okay. So, how to inject external randomness to the operating system? This is an important point because for Linux and FreeBSD, you can do this very easily. On Linux, there's a man section 4. There's a system called random. And random, there's an IOCTL. And IOCTL of, I don't know how should I read it, but the random get entropy count or something. Or random add entropy. Those two system calls can be called by a root user. So system super user can call this to inject entropy from whatever device he or she wants. And on FreeBSD, there's another system called, on a manual section 9, called random harvest. And the random harvest is unfortunately accessible only from the kernel modules. So you have to write a device driver by yourself. But I actually wrote a device driver by myself, and it's on MIT license, not MIT, BSD license, because it's BSD. BSD license, so you can take a look at the driver code if you want. And one sad thing I have to tell you is that for other proprietary operating systems, it's unable to find the same functions yet. Windows is proprietary, iOS proprietary, Android proprietary, and macOS no interface. So injecting this entropy in client machines is not easy. So before going further, I'm going to explain an algorithm called whitening. So whitening is about how to change, or better say, how to make a kind of the biased distribution into more uniform distribution. Okay, let me show you how it works. The left side, this one, is the original output from the hardware random number generator. But this is actually biased. It's not distributed uniformly on all numbers. So when you apply whitening functions, then it's like this. So it's more dispersed, it's more randomized, and it's getting better. And it's mathematically and cryptographically better. Okay. So how much randomness is enough? When you buy a $100 or cheaper generator, you may expect 10 kilobytes per second or even more speed. And this is, I think, this is practically much more sufficient, much more than sufficient for an active server. But if you generate lots of keywords, lots of keys or passwords, like when you work for, how should I say, a lot of applications. Maybe you generate SSL or TLS certificates or other things, and you need a megabps or gigabps of physical random numbers. You can buy such hardware, although they are very expensive. And I've heard that in Japanese Research Institute called the RIMS, they have a 150 gigabps hardware random generator of 1 lakh, whole 1 lakh. I don't know how the usage of that device, but there exists that kind of thing, and there are lots of people who is pursuing high speeds, the highest speed of random number generation, or high speed generation of noise. Okay. So in my house, there are actually 2 experimental systems. Number 1, FreeBSD 11, and number 2, Ubuntu 18.04. In both operating systems, it's been working steadily for more than 2 months. So I don't know whether I can call it production grade, but you can try it. You can try my code. And if you find some bug, please do feedback, and I will of course follow up. Okay. And if you only have Windows 10, you still can use this device, although the output of this device will not be in the operating system random number generator, but you can capture those output and put it into some sort of libraries such as OpenSSL or other cryptographic cryptographic library handlers. Okay, so let me summarize this talk. There are 3 points. Number 1, good randomness is very hard to obtain. You only can find less than 1 bit per second in a system. So don't expect too much. And number 2, external physical random number generator is essential for secure operation. So if you're running a server, or if at least you're running a server for a password system or something, I suggest you to use a hardware random number generator. And the third thing is that it's so common in the cryptography or random number or whatever in security, but do not invent your own methods. If you want to invent your own methods, you have to test it rigorously so that you can compete with the other products like RSA or whatever, those existing things. And it's not an easy way. Okay. So these are my references. And I've already put my slide in my GitHub repository. So you can find it in my GitHub repository. It's on GitHub at jj1bdx. And I'd like to thank GMO Pepabo for funding all this trip and all this support, especially for the Pepabo R&D Institute or Pepabo Kenkyujo people. So thank you very much. Any questions?
ありがとうございました。それでは質問のある方、挙手をどうぞ。
日本語でもいいんですけど、質問
どうぞ。英語に訳しますが、はい。
ここで出ていた十分ななんだろうランダムネスの量とかっていうのは一人で使う場合の話なんですかね。というのは私が気になっているのは、クラウド AWS とかでインスタンス立ち上げると、だってマルチテナントで他の人も使ってるか、マルチテナントで他の人も使ってる可能性があって、ハードウェアが持っている要はホストの方のエントロピープールを他の人も使ってる可能性があると思うんですけど、まあ、そういう環境では私たちは何を気をつけたらいいのかっていうのがもしお分かりでしたら教えていただきたいなと思いました。お願いします。
Okay, his question is about the virtualized environment on the multi-tenant system with many people share the same source of randomness. And yes, his question is a very good point, and it's really hard to have what do you say? Enough randomness for all of the virtual servers, and you, of course, when you run 100 virtual server in one physical system, you have to provide 100 times of what you need. This is so simple, but it's so hard to realize. Okay. 日本語でも答えます。おっしゃる通り、その仮想化したシステムでそういうことをやるってすごい大変です。で、セキュリティ問題になってますので、まあ実際に得られるランダムネスをちゃんと計測して、まあ、計測の方法はさっき、このスライドで示しましたけども、そのプロクシスカーネルランダムエントロピーアウェールっていうのこれ見てるとどんなふうにランダムエントロピーが増えるか分かるので、これを見て確認する以外は多分ないと思います。
本当にクリティカルな場合はもうハードウェアを占有した方がいい。
そうですね。He's asking if in the really critical case, using a bare metal server or dedicated server is better, and I think so.
ありがとうございました。
ありがとうございます。あと1件ぐらいですね、質問がある方いらっしゃいましたら挙手お願いします。
すみません、 日本語で失礼します。先ほどの質問は仮想っていう話、仮想化の時の危険性だったと思うんですけど、逆に実際に自分が例えば占有している時とかは、例えばインテル CPU だったりとか、IoT の方でもセキュアな NPU の中にはTRNG の回路が元から入っているようなものもあるんですけれども、それを基本的にはそれを使いなさいとか、そういうサジェスションとかはありますでしょうか。それともやはりこういうふうに外部の CPU とか NPU じゃないところの外部のものから来た方がいいのかっていうところを、もしアドバイスあればお願いします。
Okay, he's asking about there are lots of the embedded around hardware random generators such as in the Intel RDRAND and STM32 how do you say Cortex M4 or other embedded devices, and what he asked me whether those devices are better than the external device or not. Okay, I'm going to answer that. Those internal CPU random number generator has backdoors, possibly has backdoors. And this had been a huge security issue, and there's lots of discussions over there 2 or 3 years ago when Intel's RDRAND device, is it trustable? So some people want to just put Intel RDRAND instruction output into the random number generator, but eventually Linux people, FreeBSD people, both concluded no. They said no. They just take them as a source of entropy. So 日本語で答えると、要するに基本的に外部のごめんなさい、インテルのそういう CPU、インテルに限りませんけど、そういう CPU のものっていうのはちょっとつばつけて考えなきゃいけないってところあります。So let me explain once again in English. Those external devices can guarantee how to generate the random numbers by yourself. You can check it by yourself by checking all those actual circuits, because all the actual circuits are in the public domain or in the open source licensed. So that kind of traceability is very important. 要するにそのトレーサビリティとかそういうことを考えて乱数の実装っていうのをやっていかないと、本当にこれ安全なのかっていうことを人に証明してもらうっていうことがかなり大変なのかなと思います。よろしいでしょうか。
ありがとうございました。それでは先生、お時間がやってまいりましたので、質疑応答コーナー以上にしたいと思います。では再度大きな拍手をお願いいたします。ありがとうございました。